today's lesson, we are going to be looking at exponential models. So this is going to be our third type of model. We've already looked at linear and we've looked at quadratic. So exponential models. Before we get into that though, like I said, we've looked at linear and quadratic. So let's take a look at a couple examples and see if we can determine if it's linear or quadratic or neither. So in this example, looking at time in years and value, would you say it's linear, quadratic, or neither? Looking at this, we should see that we're increasing by the same amount every time. We're always increasing by $1,000 every 1 year. So this would be an example of a linear model. The first differences are the same. If we look at the next one, well, we already know how to check for linear models, so let's see. We have 50, 55, 60, 65, 70. So by looking at our first differences, we can clearly see that it's not linear. Right? So we can cross off linear. Let's take a look at the second differences. Well, from 50 to 55, that's an increase of 5. From 55 to 60, that's an increase of 5. From 60 to 65, and from 65 to 70, they're all increases of 5. With that being the case, it would be quadratic because our second differences are all the same. So again, that's something that we learned in the previous lesson. Look at the next one. Again, same idea. We know what to look for. Goes up by 50, goes up by 50, goes up by 50. I could continue and check the last two. They do turn out to be 50, but as long as we get a decent amount of them in, it should relatively be either linear or quadratic when we go through it, right? It would be very cruel if all of them were showing linear except for the very last row. So our first differences are the same. So in this case, it is linear. The next one, well, again, let's go through the same values. By first glance, we can probably assume that it's not linear. So let's go through and find the first differences anyways, because we need to check if it's quadratic. So 960 minus 640, we have 320, 1440, minus 960, it's 480. 2160 minus 1440, 720. So again, by first glance, it was probably obvious that the first differences were not the same, which is okay, but we still need to go through and figure out what our second differences are to see if it's quadratic. Again, by looking at the values, we could probably hesitate, or we could probably guess just by looking at them that they're not going to be the same, which we can already see after the first two. So we don't really need to go through and complete the last two to determine that, because the first two aren't the same, then the last two aren't going to be the same either. Or it doesn't matter what the last two are. It's already broken the rule of being or of not being quadratic. So in this case, it would be neither. So it's neither linear or quadratic. Same idea, except we're looking at an equation. So this does require us to kind of go back and see, okay, what's the equation of a line? Well, the equation of a line or of a quadratic model, let's start off with a line, y equals mx plus b. That's the general format. I can kind of see those components. I can see my m value. It's multiplying a variable. I can see the b value. It's a constant on its own. So this does fit the model or the linear model or equation of a line that we know. Next, again, this doesn't look like y equals mx plus b, so we can cross off linear right away. Does it look like a quadratic model? Well, not like the quadratic model that we looked at in the previous lesson. However, there is a key indicator that does help us determine if an equation is quadratic or not, and that would be this exponent 2. So when we have an exponent 2 on a variable, and it's the highest exponent we see, it does mean that it's quadratic. So this example here is quadratic, and this would be what we call standard form. So in our lesson, we looked at vertex form. This is an example of what standard form looks like. The key thing between both of them, though, is that we have an exponent 2. Looking at the last one, or the next one, this doesn't look like a quadratic, right? We don't see an exponent 2. We do see an exponent, though. We do see an exponent that happens to be the variable. We only have two numbers similar to our linear equation. However, the t wasn't an exponent. We didn't have any exponents in there. So that t exponent, or that exponent t, is really kind of differentiating or making this different from all the other ones. And that would be because this equation is neither linear or quadratic. We'll actually see what this is. And again, kind of guess by the title, this is actually an exponential model. And that's what we're going to be looking at in this lesson today. So if we were to look at this model, describe the relationship between the number of bacteria and time. You could say it's increasing as time goes on. You could say it's increasing drastically. Right, we can see what the values are going up by. Only small at first, 10, 20, then by another 20, then by 40, then by 80. So it is, you could say it's drastically increasing. Does the relationship appear to be linear, quadratic, or neither? Well, it does appear to be quadratic. We do have a curved line. So by looking at it, you might say, yeah, you know what, this kind of looks like a quadratic. I know quadratics tend to be like that, but maybe in our case, our model only covers that, the 1/2. Right? So because it's a curved line, based on what we know, it could very well be a quadratic model. There is one thing we can do to check, though. We know that the first and second differences, or the first differences anyway, should be different, and the second differences should be the same. So if I go back and gather the data or take the points, so 0 and 10, 2 and 20, or 20 and 20, 40 and 40, 60 and 80, 80 and 160, let's go through and find the first and second differences. So the first differences are going up by 10, 20, 40, 80. They're not the same. That's okay. That's what we kind of expected. We expected them not to be the same because we thought it was quadratic. Let's check the second differences. Change by 10, 20, 40. All right, so our second differences are different. So this is neither. It's neither linear or quadratic. It must be something else. What we're going to do next is we're going to look at the ratios. And the ratios is something different. It's very similar to the first and second differences when we were subtracting or finding the difference. However, in this case, we're going to be dividing. So we're going to find the ratios and we're going to be dividing. So if I look at the first one, 0 to 20 minutes, I'm going to divide the second y value by the first, so 20 divided by 10, and I get 2. From 40 to 20 minutes. 40 divided by 20 in terms of bacteria, and I get 2. From 60 to 40, I'm going to divide the number of bacteria, so I get 80 divided by 40, and I end up with 2. And from 80 minutes to 60 minutes, 160 bacteria divided by 80 bacteria, I get 2. So here we see that the ratios are all the same. So that means that the number of bacteria are increasing by a common multiple. And when we look at number 5, what happens to the bacteria every minute, and we can see that actually in the numbers, they double. We're going to say multiply by 2 every minute. And we actually see that value in the ratio. So by doubling, we're doubling the amount of bacteria. The ratio shows that. The ratio shows that we're multiplying by 2 every time. So that kind of gives us our pattern. Now, we're going to kind of skip ahead. So we can use an exponential model in Desmos if we wanted to go and graph that, right? Y1 squiggly line a, b to the power of x1. And it would do the exact same thing that we've done in previous lessons. It would give us a model, it would give us a strength. But let's take a look at the characteristics of an exponential model, which is what we looked at, right? The number of bacteria. So the rate of change of an exponential model changes over time. So it either increases, so exponential, we call it growth if it increases, so like the bacteria, or decay if it decreases. So exponential decay, if it decreases, the graphs would look something like this or like this. So kind of like a quadratic, except it would increase and decrease a little bit more drastically than a quadratic model would. And it's only going in one direction. Right? With a quadratic, we see going up and down, or an increase and a decrease all in the same model. With an exponential model, it's only either growing or decaying, or only increasing or decreasing, and never both. So a curved line can be drawn through the points on a graph, like we just mentioned. Neither first or second differences are constant. The ratio between y values are constant when the x values are equally spaced. So if the x values are equally spaced, we can find the ratio of the y values, which was that division, and we would get a constant ratio, which basically informs us that there's a constant percent increase or decrease over equal intervals. Just like when it was doubling, it was increasing by 100% every time. So 100% of our bacteria was what we were adding on. So similar to the model that we would enter into Desmos, exponential models can be represented by an exponential relation in the form y equals ab to the power of x. Y and x being the dependent and independent variables again. Again, we're not filling in values for them because they're there to represent any general values or any values, so it's a generalization. So that's why we leave them blank unless we're trying to solve or make predictions. The a value is the initial amount or the starting amount or the initial value, so what we're starting with. The b value is the rate of growth or decay. It's also the ratio. So finding the ratio is beneficial because it gives us a value of our model. If b is greater than 1, there's an increase. If b is between 0 and 1, so a fraction or a decimal, it decreases. So taking this information, let's just go back up and try to come up with our equation for this scenario. We know it will be y equals ab to the power of x. Because this is an exponential model, the ratio is all the same. So what's our initial value? Well, we're starting with 10 bacteria. We're going to multiply that by b, which is our ratio, or 2, and we're going to raise that to the power of x. So this is our exponential model for this equation. Now, again, I wouldn't expect you to always do that. You have Desmos available to come up with the model for you, especially if it's a weird or a unique set of data. The benefit of Desmos as well, it gives you the r squared value, which will allow you to calculate the strength. But again, the main thing from this lesson is just understanding what an exponential model is, what are the characteristics of it, how it kind of sets itself apart or differentiates itself from a linear and quadratic model, as well as what formula you need to enter into Desmos to be able to graph or come up with a exponential regression or model.